Fourier series provided a convenient frequency-based representation for periodic signals, right, where I had a capital T, and every time period the signal repeated. The question is, what if I have an aperiodic signal? What if my signal never repeats? And one way to think about this is that any signal is effectively periodic if I let that period, that capital T, go to infinity. And there are obvious consequences of that. So if I let t go to infinity, then my fundamental frequency, and therefore the spacing between those peaks that I had in my amplitude spectrum plot, f naught is 1 over t, omega naught 2 pi over t. If I let big T go to infinity, those are going to go to 0. And the amplitude spectrum plot, or what I can think of as x of f, right, big X of f in contrast to little x of t, those are going to be continuous functions of frequency now, right? The Fourier series gave me kind of discrete functions of frequency with my coefficients ak, bk, ck. In this case, I have now a continuous function of frequency. So to give you one example of an aperiodic signal, this is a recording of myself saying enme 351 into MATLAB, into the mic on my laptop. And so you can see some extra effects in here, so you can see some quantization that's been imposed on this. If we zoomed in, you could see some of the sampling that was going on with this as well. This was sampled at 8 kilohertz. But the idea is that this is an aperiodic signal, right? This is not repeating in time. And so if I'm interested in understanding the frequency content of this signal, basically the frequencies that are in my voice, I need to take a Fourier transform of this signal instead of looking at a Fourier series. So let's do a quick reminder of how we defined a Fourier series and use that in contrast to how we're going to define a Fourier transform. So our Fourier series was basically defined by these coefficients are a naught, an, bn, as well as a fundamental frequency defined by that period of the signal in question, in this case y of t. So that would be our omega naught. So 2 pi over t is our omega naught. And then we're summing up cosines and sines at multiples of that omega naught, all the way up to an infinite multiple of that omega naught. Right, and so the coefficients are defined like this, right? In this case, a naught is my DC offset for the signal. An, I'm multiplying my original signal y of t by a cosine at the current frequency I'm trying to analyze. So I'm trying to find, for example, the amplitude of the cosine part at this nth harmonic here. And so I multiply this, my original signal y of t by this cosine n2 pi over tt. And I do that over a period of the signal. And the same thing for my b term, right? I'm multiplying by my y of t by the sine part of that. And so also doing from minus t over 2 to t over 2, so over a full period of my signal. I can think of the Fourier transform definition in the same kind of way. I'm also going to have coefficients describing amplitude and phase at different frequencies, but now I don't have a fundamental frequency to keep track of because my period can be infinite for an aperiodic signal. Right, and to define that coefficient, in this case I'm going to call it a capital version of the time signal. So if I'm thinking of doing something with y of t, my coefficients are going to be used capital Y as a typical notation. So the capital indicates that it's a function of frequency, the lowercase indicates a function of time. So in this case, my y of f is going to be an integral from minus infinity to plus infinity of y of t. And instead of multiplying by a cosine for some coefficients and a sine for other coefficients like we did with the Fourier series, now we're going to use this complex exponential. And it's complex because I have this j term here, right? J is the square root of -1. And what this is giving me is one complex coefficient at each frequency, in contrast to the 2 coefficients that I had for the Fourier series for each frequency. Now, if you were really freaked out by the use of this exponential, it's not actually that bad. So I could also think of this as my two complex frequencies, so say YA of f and YB of f, and I could define those very similarly to what I did for the Fourier series. So my YA coefficients, I would be multiplying by a cosine term. My YB coefficients, I'd be multiplying by a sine term. Right? So it's effectively the same thing. I can just make the math a lot simpler and just use one coefficient. So now I just have to worry about capital Y, that's it, if I use this y of t and this complex exponential. Something that's often a little confusing for people as well is the fact that instead of going over minus t over 2, this finite, instead of integrating over a finite time period, I'm integrating over the entire time period, right? And this is because, right, I'm considering effectively a period t of infinity for my signal. And in practice, though, y of t is going to have some start time and some end time for the signal portion that I'm interested in. And finally, it's important to note that this is a continuous function of frequency, right? If I want to find my coefficient at f is 2.5173 hertz, right? I just plug f equals 2.5713 hertz into this complex exponential and compute everything, right? So I can pick any f along here. It's a continuous function of frequency. And really what the Fourier transform is doing, it's allowing me to go from any signal in this time domain, what you're really used to thinking of things in terms of time, and going from there to the frequency domain. And the frequency domain is really where we're going to do a lot of our thinking in part of this class, because we're going to be thinking about how to clean up signals that we might have that we might want to capture. And often the best way to do that is by looking at the frequency spectrum instead of the time the time plot, for example, of that signal. And of course I can go back in the other direction. Obviously I'd want to if I play around with my signal, if I do some computation on my signal in the frequency domain, oftentimes I'll want to bring that back to the time domain. And for that, I'm going to use the inverse Fourier transform. The inverse transform is fairly similarly defined. So now I'm going to be computing my y of t, my continuous function in time, as a function of my coefficients in the frequency domain, my capital Y of f. Right? And once again, I multiply it by a complex exponential, and I take the integral from minus infinity to infinity. In this case, there's no minus sign in front of the j, so that's one of the big differences here. And that's what's going to get me back to my time domain. So to give you a quick example of this is not quite a Fourier transform, and I'll get into that in the next lecture. But here's that time domain signal of myself saying ENME 351. That was captured into MATLAB. A Fourier transform was applied on that signal, and I can see that I was saying that at fairly low frequencies. I think my daughter was talking here, so you have about some higher frequency components to this signal as well that are quieter. But you can see where the frequencies in my voice ultimately lie based on looking at this plot. And if I wanted to do any kind of filtering or some kind of work on this signal, I could then use the inverse Fourier transform to move back to this time domain.